Hopefully everyone can hear me through this mask, but covering spaces is going to be my presentation. So, how do I?
Oh, wait.
Go ahead.
I need to click on it.
Oh, perfect. So this is going to be an outline of the talks, or the things that I'll talk about. First thing I want to go through are just the basic theorems, the basic properties of covering spaces, the definition, of course. Then I'm going to get into some classification, which I think is very cool and very profound. Hopefully you do as well. And finally, I'll finish with some applications of the theory that I talked about. So, go with the basics first. So just as a preamble, we want to motivate our discussion with the following idea. And this might be familiar to those who know Galois theory or field theory, but essentially, a lot of the times in math, in order to understand an object structure better, we want to look for ways to extend it to a more tractable form and see then which properties can pass back down. So this is a very powerful approach, and it's indeed what we will be using today in topology. And then a note on convention. Since we're in the category of topological spaces, map will refer to a continuous function, and space will refer to a topological space. So, first thing is the fundamental group. I don't think anyone has talked about it yet, but on a high level, it is the class, it is a set of homotopy classes of loops at a given base point on a space, say B. And the operation of concatenation, in fact, turns this into a group, introducing an algebraic structure onto a topological space. So this is very useful in terms of classifying spaces, and it's one of the principal objects of study in algebraic topology. So that's the fundamental group. Oh, and the visual unit, you can see A and B are not homotopic. They're not able to be continuously deformed in view. So diving right into the definition of a covering space, well, this is the definition. It's very chunky, so I'm not going to read it, but I want you guys to look at the visual right here. It's quote unquote called the stack of pancakes visualization. So essentially, we have a covering if we have a base space B, and then a space E and a map P from E to B, such that we have this visual. And what this visual means is that locally, the space E is akin to a collection of disjoint copies of B. Hence, the stack of pancakes illustration. So this is an open set in the base space, and that's the pre-image of the open set under a covering map. It's always going to be a stack of copies. So that's the definition. And some examples. So the first example is the least interesting one, but also easy one to draw and whatnot. So this is the trivial covering. Every space covers itself by the identity ring. This should be pretty obvious. The second example is a little more enlightening, and we'll be spending more time on it. It is the real line covering the circle S1 with a map defined by x gets sent to cosine 2 pi x plus sine of 2 pi x. So you can use trigonometric properties to show that indeed this is a covering map. Okay, so now that we know more or less what a covering space is, we want to talk about some basic properties of covering spaces. So the first, in my opinion, the most important property is that we have what are called unique liftings of paths and more generally maps, but we'll just talk about the paths here. And what I mean by lifting is this. So if you have a path, which is a map from the unit interval to a base space B, let's call it F, and you have a covering E with map P from E to B, then there exists a unique map, F tilde, unique up to base point, such that P composed with F tilde is equal to F. Or in more succinct terms, that this diagram commutes. So this is a very powerful property. You can lift paths from the base space to its covering space, where things may be easier to understand. The second property is really cool. It is the embedding property. So we can view the fundamental group of the covering space as a subgroup of the fundamental group of the base space. So the way we do this is through the map P sub star, which precomposes classes of loops by the covering map. So indeed, that sends a loop in E to a loop in B. and it is an injective homomorphism. That's the big thing. It's an injective homomorphism. So therefore, you can view it as a subgroup of the fundamental group of the base space. Okay? And if we want to categorically spice this up a little bit, this is precisely saying that the fundamental group sends base point preserving covering maps to injective homomorphisms, although that's not too necessary here. And the final property is the lifting correspondence. So this is a map going from the fundamental group of the base space to the pre-image of a base point. We define this map by sending a class of loops, F, to the endpoint of the representative loop. Obviously, you might ask, is this well defined? Because you could have picked any representative loop. And in general, no. But because we have a covering space, this is a well-defined correspondence. So these are the three big properties I want to share with you guys. And that leads us into classification. So the idea, the first big idea, again, very reminiscent of Galois theory, is that suppose B is a nice space. By nice, we mean path-connected, locally path-connected, and semi-locally simply connected, so a lot of conditions. Then, every subgroup of the fundamental group of B corresponds to a covering whose fundamental group is isomorphic to that subgroup. This is pretty huge and should remind you a little bit of Galois theory. In fact, the two are related on a more profound level. So that's the first big thing, is that we know these coverings exist and we can categorize them by the subgroup that they induce. So then that leads us to the question of when are two coverings essentially the same? Because we're talking about topological spaces, of course, you want a notion of homeomorphism, but we have to have something a little bit stronger because these aren't just spaces, they're covering spaces. So the definition is, if we have E and E prime covering maps, two separate covering maps, with or covering spaces with maps P and P prime, then an equivalence is a homeomorphism H from E to E prime such that P prime composed with H is equal to P. In other words, we want this equivalence to preserve the covering, preserve the map. And the big theorem here is that suppose we have two coverings, E prime and E, they are equivalent as covering spaces if and only if their subgroups are conjugate, or not subgroups, their fundamental groups are conjugate when viewed as subgroups of the fundamental group of the space that they cover. Again, very closely related to Galois theory. And finally, we want to consider something like the symmetries of a space. So, what I mean by symmetries are, how can I take a space, how can I twist it, permute it, stretch it, such that it covers with the same map? And that's the notion that we're trying to formalize here, and the definition is that an equivalence of a covering space with itself we'll call a covering transformation. And in fact, if you compose two of these together, it's still a covering transformation. So this forms a group under the operation of composition. So we call this the deck transformation group. You can think about it like a permutation group for a covering space. Okay, so that's great. And even better, I think, is this theorem. So this is saying if your covering space is simply connected, or in other words, that means it's what is called a universal cover. If it's simply connected, then the deck transformation group is isomorphic. Okay, it's isomorphic to the fundamental group of the space that it covers. This is, I think, pretty huge because the symmetries right here, this is very geometric, whereas the fundamental group of the base space is more algebraic. And here, this theorem ties the two together in a very profound way. So I think it's cool. So some applications. So the first one is that the fundamental group of the circle is the integers. Very quickly going to go through this, not going to go through the details, but remember we have a lifting correspondence, right? Class of F sends to tilde F of 1, okay? So because R is simply connected, we can show that this is a bijective homomorphism, aka an isomorphism. So that means that the fundamental group of the circle is isomorphic to the pre-image of the base point. But we can let the base point equal 1, 0, and the pre-image of 1, let's say just 1 under cosine of 2 pi x, that's just the integers. So, I mean, it's very elegant, very clean, and it shows you right away that the fundamental group of the circle is the integers. And an immediate application of this is that the symmetry group of the real line is also the integers, precisely adding or subtracting a natural number from R. So, I think very interesting. Oh, this is a visual. So, yep. And the second application is that we have that every map from a multidimensional sphere to the circle is null homotopic. And by null homotopic, I mean it's homotopic to the constant map. And the way to prove this, we use a little more general lifting lemma, but essentially, let's say F is a map from Sn for n greater than 1 into S1. Because of this more general lifting lemma, we can lift F to R, because R covers S1. Well, everything in R is no homotopic, because R is a contractible space. So, that implies that the homotopy that we have in R is projected down to the circle in S1. So F is then homotopic to a constant map. So, this proves our theorem. Pretty cool result, still, I think. And the final thing, and this is a very hard result to prove in algebra, but the theorem states that every subgroup of a free group is free. And the basic idea, there's two notions that we kind of have to take for granted here. One is that we have these spaces called graphs, which are exactly what you think they are. They're nodes, vertices, edges, whatever. But they can also be viewed as topological spaces. And we want to consider nice graphs, which are connected and they have a maximal tree, whatever. They're nice. Okay? So we want to consider nice graphs. And the property is that every nice graph has a free fundamental group. Conversely, every free group is the fundamental group of a nice graph. So this is really useful. And the other thing we need to cite and take for granted is that the covering of a nice graph is also a nice graph. Okay? I mean, shouldn't be too surprising, but can't really prove it here. So for the proof, you take a free group, F. Well, F is the fundamental group of a nice graph. So if we take a subgroup of F, that's the subgroup of the fundamental group of a space. Well, this is actually also a nice space. So we have a covering. We have a covering E, right, who is also a nice graph. And we know that the fundamental group of E is isomorphic to H, the subgroup. But since it's a nice graph, its fundamental group is free. So that's it. It proves that every subgroup of a free group is indeed free. And that concludes my examples, and just a final remark, I think that these examples succinctly capture the approach used in algebraic topology, namely to take an idea in topology or a problem, translate it into algebraic terms, or the other way around, and then translate it back. Indeed, this is a powerful paradigm for solving problems, and I am very glad to have been able to share it all with you. And a special shout out to my mentor, Dipendra Singh, who is a rock star.